Okay, welcome everyone. We have amazing turnout today. A lot of people I haven't seen before. A lot of people I haven't seen in a while. So welcome to the August 17th, 2021 Open Planetary Lunch. I'm Chase, the host and organizer. Our speakers today are Yuqi and Jim Head from Brown University, giving us a much anticipated update on the Tianwen-1 rover mission. So I'm very excited about this. I've not heard much about this mission since it landed. So thank you guys so much for being here. And when you're ready, just go ahead.
Okay, so what we're going to do is Yuchi's going to start out with details of the here we are with the details of the mission itself. Tianwen-1 is a really complex mission, and it's got an orbiter with a huge number of instruments on board, as well as the lander and rover. So he's going to do that, and then show a lot of details of entry, descent, and landing, and operations on the surface, etc., and give you an overview. And then what I'm going to do is, after about 20 minutes, is to talk about the geological context of the site. So this is really an amazing area. It complements everything we're doing in other exploration fora, if you will. And so this will be really interesting from the perspective of what it's going to tell us and is telling us about the geological evolution of Mars. So let me ask Yuchi to take it away, and I'll see you in a few.
Yeah, and I'm going to talk about the Tianwen.
You're muted, Yuqi.
Oh, sorry. Yeah, we just need one mic. Today I'm going to talk about Tianwen-1 mission and the Zhurong landing site. And I'm from China University of Geosciences. And what is Tianwen-1 mission? Tianwen-1 mission is China's first Mars mission. It is composed of orbiter, a lander, and a rover. This is the largest object that people send to the Mars because this is a 3-in-1 mission. So the mass of this object is very big. It's weighs 5 tons. It is the largest object people send to Mars. And in July 23rd, Tianwen-1 was launched from Wenchang Space Launch Center. And after several orbit corrections, the Tianwen-1 orbiter entered the Mars orbit. These are videos taken when the orbiter performed capture burn in February 12th. After that, the Tianwen-1 orbiter was captured by the Mars and performed the Mars orbiter operations. And in the way to the Mars, Tianwen-1 orbiter released some Wi-Fi cameras, very interesting small things, dropped away some Wi-Fi cameras and to take these selfie images. This image was taken on October the 1st, 24.1 million kilometers away from the Earth. And this is the mission profile. And after the Tianwen-1 orbiter entered the Mars orbit, it didn't land directly like the Perseverance rover or the Curiosity rover, but it performed some parking orbiter operations. So I think the voice sounds too big because they're the first time since I performed this kind of Mars mission. So it need to stay in orbit for around 3 months to perform surface investigations, especially impact craters and dust activities, because these two things will be hazards if do not dealt with very well of the lander. So it stayed in orbit for 3 months, and after 3 months, the lander and the rover performed a descent. And performed entry, descent, and landing. I think we can watch these videos about the strategy of and land on the Mars surface. And gradually land is very similar. It will stop at a certain distance, around 200 meters, and volcanic underneath. And then gradually use the geometry and you will see that different from the curiosity and different from the perseverance rover, the thruster directly hit the ground, and it has some consequence, which we will see. We will see in a minute. And then let's take a look at this very interesting and tremendous videos taken by the lander. These are the parachute. This is, I think, this is the heat shielding, and these are images taken by the landing camera. And then finally touch the surface, and you can see this like feather plume features. The EDL process happened in May the 15th. And then after the landing, the rover was deployed 1 week after the landing because the engineering team want to check the health condition of the rover, and the rover and the lander to check their health conditions before the rover was deployed. And these are some videos taken there. You hear some voice. This real voice recorded by the mass climate station on board the rover. This voice, and you can also see these videos are taken by the Wi-Fi camera. The Wi-Fi camera was dropped away by we can watch these two videos again. The Wi-Fi camera was dropped away by the rover. And when the Wi-Fi camera was dropped away, the rover moved back together to stay with the lander, and they take several sub-file images together like this one. Actually, this is a video. The rover was adjusting its position to a good position to take images.
Yuqi, real quick, when there's a video playing and it has audio, we can't really hear you speaking.
Yeah, I think. Jim, maybe mute you.
Okay.
Yeah, and
No, we can't hear you speaking at all.
We're making an adjustment here. Stand by.
Oh, okay, thank you.
yeah. Oh, and close your voice.
Now there's really bad feedback.
One mic and one voice. So could you hear me?
Yes, it sounds clear now.
Yeah, sorry, I think we'd better not play videos anymore. It's very.
Let's do it.
Yeah, and these are several images taken by the rover. Yeah, we don't have videos. Yeah, it's a good thing. And these images taken by the rover, the Zhurong rover, after they landed on the Mars surface, and we can see that. I just talk about when the thruster plume hit the surface, it has some consequence. This is a consequence. There's a big hole dig by the thruster plume, and there are some feather features radio to this hole. And this phenomenon, if do not deal with properly, the lander will just fall down. And you know, the Perseverance rover landing a different strategy and do not this problem. But in the future, when like people want to launch from the Mars surface or land up to the Mars surface, this phenomenon should be dealt with very carefully because the lander will fall down. And except for this big hole, there also another very interesting thing. This is a flag of the souvenir of Beijing Winter Olympic Games. It is here very small flag. One is a panda and another is a lantern. And let's just take other images. Took a look at other images taken by the rover. This is the panoramic images, and in this panoramic images, the most permanent features we see is just the rocket exhaust feature. This two dark linear feature are the rocket exhaust features, and you can not only see from panoramic images, you can also see this from the HiRISE images. This image was taken by HiRISE, and you can see the rocket exhaust feature directly. And except for these two permanent rocket exhaust features, I want to bring your attention to this small black dot here. This small black dot here, this is a parachute. This is a parachute, the parachute of the Zhurong rover. And actually, the Zhurong rover has traveled to this place and take images of the parachute. And except for this parachute, there is also a pillar cone. The pillar cone is here. This is a pillar cone, and the pillar cone sand dunes like these features are the most permanent features in this region. Let's talk about something about the science. For the Tianwen-1 mission has 5 scientific objects. One is study the characteristics of Martian topography and geology, study the surface and subsurface water ice distributions, investigate subsurface surface compositions, study ionosphere climate, study physical fields, etc. To accomplish these scientific objects, there are different payloads installed on the Tianwen-1 orbiter and the Zhurong rover. And also you can see from the scientific objects, the Tianwen-1 mission and the Zhurong rover is a geologist, is a geophysics, but not a geobiologist. This is several payloads on board the Tianwen-1 orbiter. There are 7 payloads on board the Tianwen-1 orbiter, including moderate resolution image camera, high resolution image camera, investigation radar, and mineralogical spectrometer, magnetometer, ion and neutron particle analyzer, and energetic particle analyzer. There are 7 scientific payloads on board the orbiter, and I will highlight 3 of them later. And there are another 6 payloads on board the rover. There are camera, there are multispectral camera, there are penetrating radar, surface composition detector, rocket magnetometer, and climate stations. We can see that some payloads have similar functions on board the orbiter and the rover. That is because we want to compare the data obtained from the rover and the orbiter, from the orbiter and the rover. And I will highlight 2 of them later. This is the first payload I want to highlight is high resolution image camera. This camera has several working modes, and for the imaging modes, it can detect for panchromatic imaging mode. It can image the surface with resolution better than 0.0 meters, and if using the mode with colors, it can image the surface with resolution better than 2.0 meter. And we can also see that it has 5 bands. The panchromatic bands is a broad band, and another 4 bands has wavelengths of this. And we can see that from other numbers, if the high resolution image camera image a surface with the panchromatic imaging mode, it can acquire very high resolution images, and the number is similar to the HiRISE camera. And if it want to image a place with full spectrum, the resolution will be reduced, but maybe you can get some composition information from this imaging mode. And actually, the high-rise images obtain images of the landing sites, and here are the landing sites images. And already the high resolution image camera already acquired the full coverage of the Tianwen-1 of the Zhurong landing site. Another instrument I want to highlight is the mineralogical spectrometer. This is a spectrometer on board the orbiter, and it is a typical visible near-infrared, middle-infrared spectrometer. For the visible near-infrared spectral range, it has a spectral coverage from 0.3 nanometer, 0.3 micron to 1.0 micron. And for the near and middle infrared spectral range, it has a coverage of 1.0 to 3.4 microns. And the spectral resolution is here. And compared with Prism on board a mass reconnaissance orbiter, the spectral resolution is better, but the spectral resolution is worse for the mineralogical spectrometer on board the Tianwen-1. And right now, the Tianwen-1 orbiter is in a release orbit, but after the nominal mission of the Zhurong, it will enter a remote sensing orbit. When the orbiter entering the remote sensing orbit, it will give the mineralogical spectrometer for every orbit, it will give it a chance to image the Mars surface 26 minutes. And here is the design. And after this 26 minutes, it can be cooled down when it much fire to the Mars. And except for this instrument to measure the Mars composition, we can also acquire inside data from Mars surface composition detector. This Mars composition detector is composed of 3 major components, including laser-induced breakdown spectrometer, a shortwave infrared spectrometer, and a calibration target. And for how does it to measure mass compositions? The engineers did a lot of pre-flight calibrations and also bring a calibration target on rover. This is in-flight calibrations, and this is installed place for this calibration target. And we can see that it has 12 calibration materials, including apatite, dolomite, etc., olivine, basalt, etc. These targets can also help to decide what the composition it is measuring. Except for the calibration targets, it also the engineers design a CNN network for element analysis. So machine learning is everywhere, and this is several numbers of the mass composition detector and the supercam and CamCam. We can see that the mass surface composition detector, CamCam, and the supercam has similar spectral coverage, and the calibration target number is similar for mass surface composition detector and half less than the supercam, half less than the supercam. And the mass surface composition detector has a spectral coverage, has a spectrometer. Supercam also has a spectrometer, but the CamCam doesn't have a spectrometer. So the function of mass surface composition detector is between CamCam and the supercam, and it's also variable for if we can compare the LIBS data between the data gathered by different payloads. It will also be very valuable. And the radar, there is a orbital radar, and this orbital radar has a resolution of has 3 channels: low frequency channels, high frequency channels, and it has a resolution about 100 meters horizontal resolution and a penetrating depth of 100 meters for Martian soil, 1,000 meters for water ice. And why we want to carry this orbiter? That is because there's lots of evidence of subsurface ice in Utopia Planitia where Zhurong landed, and there is also other double layer craters, which is another evidence of subsurface ice. And there is another. This is a radar on board the rover. We can see that it has a low frequency channel, high frequency channel, but both of them will be very useful to study the subsurface ice. And we did a lot of work in Basin to prepare the data processing of the Zhurong rover, because the Kardan Basin is a very ideal mass analog site. And the last thing I want to mention is the data policy format and policy. The data was acquired by China's deep space network with 4 major antennas and processed in this way. And the level from level 0 to level 2C, and the scientists can get level 2 data. They are corresponding to calibrated data of the PDS data level. So all data acquired by SINSA are after transformation, include transformation, archived in PDS4 data. And the international scientists can finally get the data 12 months after this mission, and all the data will open to public. But right now, Chinese scientists can apply the data obtained by the Tianwen-1 mission from this point. And when the data are open to public, you can go to this website to download them and check other information. So this is the Tianwen-1, the Zhurong landing site is in the southern Utopia Planitia, in Borealis formation. And this is the traverse map of the Zhurong. Right now, Zhurong has traveled over 800 meters in August 15th. And it's heading north to the assumed uplands and lowland shorelands. And Jim right now will talk about the landing site and its scientific meanings.
You want to quit sharing?
Yeah.
Okay, thank you very much, Yuqi. You can see this beautiful payload on both the orbiter and the lander is really, well suited to solve a whole series of scientific problems. Okay, stop sharing. Sorry, 1 second here.
I think I already stopped my sharing.
Okay. Okay, that's okay. It's just okay. We're good. Chase, we good to go?
I think so.
Okay, full screen.
Yeah, that looks good.
Okay, so again, this is a really incredible landing site, and I want to try to lay the groundwork here for the kinds of things that this will be able to attack, and is in fact attacking right now with its roving and also orbital mission capabilities. So this talk I want to give today is really related to, it derives from a talk I gave in 2018 at the Tianwen-1 team meeting in Zhuhai. And I was invited by Chunlai Li, who's one of the key people in NAOC, to talk about the 2 different sites and which would be preferable in terms of the landings, et cetera. So, we had a great discussion, and the consensus, from a scientific point of view, was towards the east there, site 2, for a variety of different reasons. That was the one that was finally selected. Of course, the engineers had a very strong say in all this as well, depending on altitude. And as Yuqi was pointing out, the orbital capabilities for several months as the site was examined and finally chosen. So wonderful entry, descent, and landing. You could see from Yuqi's videos the basic way in which this does differ somewhat, in fact, quite differently in many ways from the NASA and ESA landers. So we have great capabilities here. So I want to go on and talk about exactly where we are. Indeed, and talk about some aspects of the global picture, the geological history of Mars, and how this mission is really going to help. So where are we? We're right in the middle of the northern lowlands, if you will, not in the middle of the northern lowlands, but in the northern lowlands, well into the northern lowlands, in the Utopia Basin. And this is really important because both the northern lowlands, as you can see here in this MOLA topography map, and also the Utopia Basin are 2 fundamental aspects of the characteristics of Mars geological history. So let me just go on a little bit and talk about that. So the Zhurong rover scientific exploration addresses really some of the most fundamental scientific questions, and I'll list them here briefly and then talk about some of them in detail. So
asteroid, comet, and moon.
Was that a question, or was that just a?
I think it's resolved.
Okay. Okay. So let's Noachian and also Hesperian oceans. So this is both of these proposed oceans. In fact, the Zhurong lander is below the shorelines for both of these. We also, the question of life on Mars, well, where else are you going to find it if not in the oceans? Evolution of Mars' atmosphere, the climate history of Mars, the role of nonpolar glaciation, a series of enigmatic geological features that we can talk about, and particularly the pitted cones. And again, the whole origin of the northern lowlands and the geological and mineralogical evolution of Mars. These are all really fundamental things that, in fact, the Zhurong rover in its landing site can address. And of course, all of this is paving the way for Chinese Mars sample return and human exploration, which we'll touch on at the end. China has definitely plans to return samples from Mars, and these data and all the other data from the NASA and ESA landers and rovers will be really helpful in that too. And of course, China has recently announced plans for human exploration of Mars as well. So it's really going to be great to be able to take advantage of all these capabilities internationally to understand what's going on. So I want to talk about a couple of these questions here. Let me start out with the major physiographic features, okay? So it's clear that, you know, the northern lowlands are one of the most fundamental aspects, and indeed the dichotomy boundary, as well as the Utopia Basin. So this whole area in the north, okay, why is it low? What's going on? And then why is this circular feature here? It's clearly an impact basin, but it differs from the near contemporaneous Hellas Basin and many others in these areas here. So what's going on there? So basically, the Zhurong rover is in a position where it can potentially address some of these issues by analysis of samples and just looking at the stratigraphy and so on. And of course, we have a lot of information about the geological history. These are the major eras in Mars history. We're all familiar with the details of what went on in the Noachian, Hesperian, and Amazonian. And the point is that the Zhurong lander is in a place which really treats a significant number of the issues that came up in this geological history. So, and the questions that arise. So it's in a really great position, more so than many other landers, if you will, in the previous history of exploration of Mars to address some of these issues. We can also address the mineralogical history, you know, on the basis of the work of Jean-Pierre Bibbring and his colleagues, and Christensen and Murchie and Mustard and others. You know, we kind of know the mineralogy, Bethany Ellman and others. And so the key here is that we actually can look at the differences, because in fact, the units that we're talking about here deal with both Noachian clays with potentially Hesperian sulfates and again, Amazonian deposits as well. We also know that the climate history of Mars is thought to have been warm and wet in the late, in the Noachian and perhaps into the Hesperian for a transition. Phyllosilicates to sulfates and then on to anhydrous ferric oxides in the Amazonian period. So here is a position, you know, we have units from all of these in the Zhurong lander area there. We can also look at the characteristics of the hydrological history. You know, if indeed early Mars was warm and wet, then there was a vertically integrated hydrological system. So we should be seeing plenty of water in this area here, and maybe the drainage from the valley networks, maybe the Noachian Ocean, before Mars and the transition period developed a global cryosphere, we can see evidence of these types of things. So again, we're in a great position here in this landing site to think about some of these issues. And of course, the atmospheric history is just a big mystery on Mars. It's thought that might have had an atmosphere, something of the order of maybe even Earth's 1 bar atmosphere. And of course, we know now it's 6 millibars. So, you know, what happened in between? This is really kind of critical. Were there oceans in the past history? Did they go away? Is that where the polar caps represent right now? These are fundamental issues that we really don't have a good handle on, and Zhurong rover is in a position to address aspects of this as well. So the sequence of events in Mars history, you know, I'm not going to go over this, but this is kind of like, you can study this in detail if you wish. These are some of the major features in post-accretion, magma ocean, and so on, from the pre-Noachian, Noachian through the Hesperian and into the Amazonian. And actually, the Zhurong lander is in a position to address many of these issues. I'm going to point out a few of them here to give you an idea of what we hope will be coming in the coming weeks. Of course, the first is the sequence and timing of conditions on early Mars. When did the dichotomy boundary form, and how did it form? That's you can see in the MOLA data how, you know, there's a big depression in the northern lowlands there. How did that form? And of course, there are a number of papers that came out in 2008, which in fact addressed the question from the point of view, maybe an oblique impact formed the Borealis Basin, and that's what formed the dichotomy boundary. So, wow, if we can find any evidence for, impact ejecta associated with these features and et cetera, then, and also sample return potentially in the future from this type of area, it's really important. So think about this site not just as an exploration site, but also pretty much like Perseverance is at least scouting and not being able necessarily to collect samples to bring back, but scouting, is this the best place to go to address some of these more fundamental questions? This was followed, of course, by the Utopia Basin, okay, not too far after the origin of northern lowlands. And you can see here the Utopia Basin, where the bright red star here is, that's a large depression here. It clearly happened after the oblique impact or whatever formed the linear aspects of the northern lowlands. And, this basin here, Utopia, is very shallow compared to Hellas. So what's going on there? Was that something related to maybe the thermal structure after the Borealis Basin formed? Or is it related to sedimentation, for example, from the oceanic sediments in a Noachian? Or maybe there's ice filling it up, okay? This is why we hope that the ground penetrating radar on the Zhurong rover and also from orbit will be able to help address this kind of question. And of course, we have the whole era of valley networks, closed and open basin lakes. Perseverance is exploring, in fact, one of these at the present time, Jezero crater. These seem to represent and have been interpreted to represent the warm and wet climate optimum period where water runoff dominates over the, in fact, infiltration. So we have warm and wet, transitional, and the climate history is really critical as well. And we'll be able to address some of these things in this particular area. And in case you think there isn't a difference between the warm and wet and cold and icy hypotheses, here's one on the left, the warm and wet, with from Lua et al., 5 kilometers water global equivalent layer, whereas the cold and icy, a number of workers have suggested that, wow, there's an adiabatic cooling effect when the Mars atmosphere exceeds about several tens of millibars in atmospheric pressure. The water is going to go to the highlands and snow out because it's 225 K mean annual temperature. And then, basically, maybe you only have hundreds of meters of water GEL. And transient events might heat and melt that to create the valley networks and so on. So this is an issue, and any evidence we can find in the Zhurong rover area is important. And was there an Noachian Ocean in Utopia Basin and the northern lowlands? This is really important. And I pointed out that maybe that's sedimentation, maybe it's even frozen ice left over. We know from Charade data that we can preserve ice on Mars for several hundreds of millions of years below a covering of fragmental silicate debris, as we see in Antarctica as well. And so, maybe there is water ice there. So this is going to be a role for, in fact, the ground penetrating radar to play, et cetera. So these are, again, fundamental questions. One thing we see, though, is the valley networks shown here in blue with the open and closed basin lakes and open in red and closed basin in green. Basically, the valley networks don't seem to drain into the northern lowlands or into the Utopia Basin. They seem to drain into these open and closed basin lakes, such as, in fact, Jezero, but they do flow out of them, but they don't seem to be robustly filling the northern lowlands. So that's a question. So that's something we need to look into. So we explore Utopia deposits, that's why we want to look for dolomites and carbonates and other kinds of things. Are there in fact evidence for sediments of Noachian age in the northern lowlands that might indicate the presence or absence of an ocean? That's really, really critical. Now, there of course is an atmospheric transition at some point here between the Noachian, where it's thought to be a higher pressure CO2 dominant atmosphere, and down through the Hesperian. We also know the Hesperian is in fact a time of volcanism, okay? So there was a lot of volcanic activity in the Hesperian with the early Hesperian ridge plains and other related features. And here you can see a view of the northern lowlands looking down on Utopia and related parts of the northern lowlands. And basically, essentially significantly a very large amount of the northern lowlands, including Utopia Basin, was paved with Hesperian ridge plains. We know this from the detrended data and also the kinds of crater work that Herb Fry has done to look at obscure covered craters covered largely by, in fact, volcanism. So indeed, following the Hesperian ridge plains, we had the outflow channel formation, okay? So now we're in the Hesperian, but we don't seem to see any outflow channels that go into the Utopia Basin. So we see them going into the northern lowlands, that's for sure. We've explored those with Viking-1, Pathfinder, other types of other related missions, and will with the ESA mission coming up in the near future. But we don't see any big valley networks, big outflow channels going into, in fact, the Utopia Basin here. So what's going on there? Why don't we? And what's happening there? Okay, a big question. What we do see is the Vastitas Borealis formation, which is a unit that covers much of the northern lowlands. In fact, that's the unit on which the Zhurong rover sits, as Yuqi was pointing out. So we have a bunch of questions. You know, how often did the outflow channels form? How much water was in each event? Where did the water pond? What was its fate? Does the Vastitas Borealis formation represent the sediments? You know, where's the water now? These are fundamental issues which we hope Zhurong will be able to supply some evidence to help sort out. Of course, Utopia is the site of tectonic features as well. It's well known for years. The Wrinkle ridges, we could see these in Viking and pre-Viking data actually, polygonal grabens, et cetera. So the whole tectonic history of the Utopia Basin is important. So we're hoping to see and traverse over some of these fractures and some of these structures and distinguish them from contraction crack polygons related to ice versus tectonic features versus buried features, buried by sediments and ice, et cetera. So there's a whole host of different types of things that we can look at in the Zhurong rover landing site with tectonics and deformation of Utopia Planitia floor. And of course, we have volcanism from the east, okay? It's interesting that from Elysium, okay, we have indeed Lahars coming in. These are these large units here you can see in the color. And there seems to be mobilization of water-rich volcanic sediments here that are coming hundreds and hundreds of kilometers out into the northern lowlands, in particular into the Utopia Basin. Now, Zhurong is down here. It's not right at these. It's unlikely to be able to get to them, but nonetheless, these have consequences and also related effects, which we're hoping to be able to sort out as well. And again, the volcanism continues on, as you can see here, from Elysium, even into, in fact, the Amazonian. So this is really important too, to look for the volcanic features. And maybe these pitted cones are indeed related to this type of volcanic activity. There's also ample evidence in the east along the edge of the Utopia Basin for volcano-ice interactions, dikes coming into ice and sediment, ice and glacial-like deposits and causing melting, et cetera. There's a whole series of papers on this. Gro Peterson, who's now in Iceland, has worked on these, as well as De Pablo and Komatsu, et cetera, and the pitted cones. Really fascinating work, and surely we're going to be able to get to one of these pitted cones, at least one, with the Zhurong rover. Now, in the Amazonian, as everyone is familiar with, is a period of course, Mars is always a period of climate change, but Mars history is. But in the Amazonian, we know that when the spin axis tilts, that is, obliquity increases, polar ice is mobilized and transported into more towards the equatorial regions. We know this at all scales and at all times. We've really been able to document this over the years. And in this map here, you can see in the red boxes, the latitude-dependent deposits, concentric crater fill, latitude, low-bake debris aprons and lineated valley fill. All of these things we've seen here and documented, and this is right in the area of the Zhurong rover. So we know that in the Amazonian throughout, there's a lot of activity where snow and ice was coming into the Utopia Basin. So that's another thing to look for. And when the snow and ice does come into the basin, you know, we know that many cases, impact craters are continuing to happen and are superposed on the snow and ice. And we can learn from these, because what happens is that when an impact occurs in the snow and ice, it ejects material from the substrate below the snow and ice, and this forms pedestal craters like you see here, and they actually preserve the ice underneath. So if we're lucky, we can go up to the edge of these and study the icy record that's preserved by these pedestal craters. So this is another area here that we're looking at in detail. Well, what happened in the Utopia Basin? Well, a lot happened in the Utopia Basin. I mean, here is the geological history of Mars, and each one of these things represented something that happened in Utopia. Now, the faint of heart might throw up their hands and say, well, how the heck are we going to sort all this out? But again, we've got great instrumentation on this, the ability to do long traverses, and we're really clear that there's a lot of opportunity to address many of these issues. So this is very exciting, and it's very different than the other landing sites that we've landed at previously. So what are the outstanding questions? Well, the age and origin of the regional plains, what is the floor of Utopia Basin? Are they Vastitas Borealis, ocean sediments, Amazonian age plains? Are they reworked or veneered glaciers? These are the kind of things that we're investigating, and the ground penetrating radar is going to be really important. Is there evidence for a former ocean? We might look for any of these types of things here, any kind of drop stones, or maybe glacial meltwater or salts, evaporite, sediments, etc. Any evidence of fossils or trace fossils? These are the kinds of things that clearly one wants to look for to address that. And what's the Amazonian climate record in Utopia? We know that obliquity has changed. We know there's a lot of evidence going right up to the most recent period, a few millions of years ago, in which the obliquity, although the mean obliquity has been relatively constant, the amplitude of the obliquity has changed significantly. So this indeed had an effect in the last few millions of years on certainly the Viking 2 site in northern Utopia, and definitely it's going to have an influence on the Zhurong site as well. So we need to sort that out as well. So another thing is the pitted cones I've referred to several times. Determining the origins of pitted cones would really help to resolve a major enigma here. Okay, so this isn't just, like, oh my God, we have 10 different hypotheses. They differ so much that resolving this question is really going to help us understand a lot about these pitted cones and their distribution. Are they volcanic? Are they pedestal craters? Are they pseudocraters, spring mounds, tuff cones and rings, mud volcanoes, pingos, etc.? These are quite different hypotheses, and I think we have a chance of sorting that out as we visit these things. So a question we will ask is the diversity of rock types, and what is their stratigraphic sequence? So again, what are these different kinds of rock types that we'll be seeing here? We're already starting to see some of these, and the documentation will be coming out in the near future. And so this is the kind of thing, we should be able to tell glacial till from impact breccias, from volcanic tuffs, from evaporites and sedimentary rocks. And this will be the challenge as in the coming months as Zhurong continues its exploration of the northern lowlands. So how can Zhurong address these questions? Well, there's so many different things it can do here, and it provides access throughout the site. And here's 10, okay? You can come back and look at these a little later, but I mean, the plains, the age and origin, the pitted cones, the lobate features, you can see illustrated around a corner here, the edge of this, pitted cones, a lot of the features, these embayed features here, these pedestals, the transverse aeolian ridges, we see evidence for curved ridges of uncertain origin, impact craters that can reveal stratigraphy in the walls and so on. So it's really, really exciting, because this is a place where we see so many different aspects of the history of Mars laid out in front of us, and it's really an important landing site to be sure. So finally, I want to point out just a couple of things here, which is, as you can see from this map of previous landing sites, the Zhurong rover is in fact in an area that is different than the others. So Jezero crater here is in fact an open basin lake. As you know, InSight is up on the plateau here. Here's Spirit and Curiosity, Viking 1, Oxyoplanum here for the upcoming ESA mission, and Pathfinder and so on. This is below Contact 1, for both the Noachian and Hesperian Ocean. This is below what we're have been interpreted to be the shorelines of these features. So not only is it fundamental in terms of the early history of the formation of the northern lowlands, the dichotomy boundary, and also the Utopia Basin, but it's really, really important in terms of the question of oceans on Mars. Was there a Noachian Ocean? Was there a Hesperian Ocean? Were there no oceans? What's going on here? So this is a beautiful place. It complements beautifully the other landing sites such as Jezero and the Oxyoplanum site, et cetera. And this will really be great in the future. So finally then, this paves the way for the Chinese Mars sample return mission, which will happen towards the end of this decade or into the next decade, and also for human exploration, okay? And if you haven't heard about human exploration, at the GLEX meeting recently in San St. Petersburg, President of Chinese Academy of Launch Field Technology. They're the people that get us there, folks. They announced their human Mars exploration transportation system. Beautiful, beautiful. I think Elon Musk is probably quaking in his boots as he listened to that. So lots of great activity going on, and this is a great opportunity. And I just want to close by saying that remember that, this, if you have any questions, please get in touch with myself or Yuqi. And remember that these data are available. I think a common misconception about the Chinese program is that it is closed, that it's hard to get the data, et cetera, that nobody says anything. It is quite the contrary. When I gave this talk, or a longer talk actually, in Wuhan on the day of the launch of the astronauts to the Chinese space station. And it was just absolutely fantastic. So I gave half an hour taikonauts to the space station, and then we went back and finished the talk and had a great discussion for quite a long time. So again, Yuqi pointed out the website you can go to, the Chang'e 5 data, and all the Chang'e data is also available at these websites. So please do welcome our Chinese colleagues, and also, take advantage of these new data, because the universe and the solar system, it's a large place, folks, and it's much better to share than it is to duplicate in the future. So thank you very much, and Yuqi and I are happy to answer questions.